Hi everyone, welcome to ManCave. I got this oscilloscope on eBay for £20. It's a Tektronix 2201. It's a mixed analog and digital storage oscilloscope. You can switch between the storage and non-storage mode. So it's a good little scope. It's only 20 megahertz, but you know, it's a good little scope to play with. And I bought it as faulty, so that gives me a little chance to play with it and see if I can figure out what the fault with it is, and you know, maybe get it to work and have a nice little scope. I only paid £20 for it, so even if I don't get it to work, you know, it will make an interesting teardown and a repair video. So I'm gonna open it up, have a look inside, and try and troubleshoot the problem, and then hopefully fix it. So just stay with me if you're interested, and let's get into it. So a little bit about the scope itself. As I mentioned, is a Tektronix 2201. It's from the famous 22000 series. It's a 20 megahertz analog and digital storage oscilloscope, 2 channels, and it's got 10 megasamples sampling rate, and the minimum resolution is 50 nanoseconds division and 5 millivolts per division. I was told that it has a faulty power supply, so I'm curious to see whether that's true or not, but we're definitely gonna power it up first and see whether we get anything at all, and then we take it from there. Alright, so let's power it up. We'll plug in the mains lead. And press the power switch, and nothing. We don't even get the LED on. Nothing. So yep, that's definitely faulty. Absolutely nothing. So the first thing you want to do really is to check the fuse. I'm sure they have checked the fuse before they sold it as faulty, but you never know. It's always worth doing that. Yep, fuse looks okay. I'll just give it a quick measure. Yep. So the fuse is fine, unfortunately, or fortunately for the sake of the video. Okay, the switch, there's a switch at the back for the 230 and 115 volts. It is in 230 volt position, so that's fine. Now, I was lucky. What I got for my 20 quid, I also got the option of the serial interface, so that's a little extra that I didn't expect, because it was not advertised as with the option. So let's take it apart. To do this, you got to take these 2 screws off. That should take the back panel off, and then there should be 2 screws on the side as well, and that will allow the case to slide back. We're using a Torx. Is it Torx 15? I like the construction of these tech scopes. They're really good for serviceability, really easy to open. So I should allow us to remove the back. Yep. And then I have one screw here. And one on the other side. Right, I can also see that there is a little screw in the serial interface board. I'm going to take that out as well, just in case. The board doesn't come out, so I assume it's going to just slide out. And there's a little catch right here. You have to make sure you lift that up a little bit to allow the board to come out. I'm going to zoom in on that a little bit. See that little catch there? Just there. So once you lift it up, the case will just slide off like this. Okay, put that to the side. And here it is. Oh, beautiful little scope. Okay, so what we've got here is there's several boards. There's a main board at the bottom. There's a digital storage board right on the top here. You can see on the front as well that the buttons go directly to the digital storage board. So these are all to this one is, for example, to turn on or off the storage mode. And then the second from the top board is the optional serial interface board. This just comes off. So that's the optional serial interface board. Then another board here is the attenuator board. Right at the bottom is the main board, which has several sections. There's a power supply at the back, and in the power supply section there's a vertical board here, which is the mains input board, and there's some filtering there, and rectification, and the main DC filter cap there as well. And then we have a transformer here, and the main switch mode power supply section here. We can take off the digital storage board. Again, same screws, Torx 15. Take them all off. What I normally do is when I'm taking apart something like this with different bits and pieces or different length screws, like for example this middle one is quite long. I saw a little bit of that. So if you compare these two screws, they are a different length. So what I normally do is I take a photograph. I put the screws up here. Once I take them out, first I take a photograph with the unit assembled, and then with the screws laying down sideways next to each hole that they belong to, like so. And that will help me during reassembly to make sure I put correct screws in the correct place. And you can see, for example, this one here, it's got a little washer underneath, and it's got this little plate here as well. So yep, you want to make sure you do put these back in their place. Okay, so another one there, and the last one. Really, you want to be organized when you do something like this, because you don't want to be left over with some screws or other little bits and pieces. Okay, so these are all. Now I will take a picture and then take all the screws off, all the little bits and pieces. And also don't risk it, don't just put them somewhere on a table. What I normally use when I disassemble you know, equipment, I'll take one of these and I put the bits and pieces in there. You can stick those in there if they fit. Okay, and put it aside. Now, in order to remove this board here, you need to remove the buttons. So to do that, I'll just use a small screwdriver. Just push it off like that, and I should be able to take the button out. Or even if you don't, just put it to the front, and that will allow you to remove the board. Okay, so again, just like that, gently, always be gentle there. You don't want to damage these because it's not so easy to get them, they're custom parts. You'll have to probably get it from some other broken scope. Okay, so the next on the list is the connections on this side. There's two wires here which will stop you from taking this board out, so just disconnect them. I marked them already as 1 and 2, and I marked the corresponding connectors on top here as 1 and 2, so I'll know how the wires go back in when I'm trying to reassemble it. And we also have the serial board connected. Okay, there's a little screw here on the side which I haven't noticed. There's this one here, that's for the serial board. So that's Torx 10. We'll remove it. Okay, I actually turn this so you can see it from the front. It'll be more interesting. Because what we've got here is we can flip the board up like so on these little service stands. Okay, and that will give you a very nice access and ability to service the kit while everything's connected. Now, because we want to have a look inside, I don't suspect the digital board or the serial interface board to be faulty. We're going to take them out to have a little bit better access to the main motherboard. So first of all, I'll remove the serial board. There's just two little clips on the back there, and that just pops out. And now I take out these all these connectors, and that will give us better access to the back. Okay, so to remove them, same as the side ones, just pull it out like so. You always have to push on the connector itself in order to remove it. Okay, and now you just pull the board out. That's the digital board. Lots of 74HC logic there. I'll just show you a close up. Okay, so you put it to the side and remove the buttons as well so they don't fall off. We don't lose them. Put them to the side. Okay, so with the serial interface and the digital storage boards removed, what we can see here is the attenuated time-based board, which is the one on top here, and underneath there is the main board, which is split into several sections. But what we are concerned about at the moment is the section here, which is the power supply part. So this is the IEC inlet, which goes into the main transformer over here, and from the main transformer back to the main input board, and we have a 4-diode rectifier and a filter capacitor, and from there the rectified voltage goes to the main power supply board. The switch 1 power supply will generate all the various voltages that are required by all the circuitry, and it will then distribute all the voltages to all the boards. So once you have eliminated all the simple faults like blown fuse, then you can progress into a board level troubleshooting. And then the first thing really you should do is just have a good look around the board and have a look for any obvious things such as cold solder joints, disconnected cables or wires. Obviously we have some here, but anything else that you could see that you haven't done yourself, and you know, any blown up components, charred or with a hole in them, etc. Any visual indication that may suggest that the fault is you know, in a certain area of the board. The next thing we're going to do is, since we don't have a service manual, we're going to flip this over and have a look at the back. And we'll zoom in a little bit. We have a look at the silk screen, which you know, the board's been laid out really well here. You can see some bodge wires. Obviously there's some pins which have no connections to them on bottom or top whatsoever, so they had to bodge it up after the manufacture instead of respinning the board again. But also you can see, apart from all the component markings, is you can see the various test points for voltages. So if you look here, for example, you won't see that one. It's minus 5.2 volts test point here. This one here is 5.2 volts. Let me zoom in a little bit. Then we have minus 8.6 volts, plus 8.6 volts, plus 38 volts, and plus 100 volts. Now this is very helpful if you don't have the schematic, because you can obviously power up the circuit and just measure the voltages at the test points, and this will obviously indicate whether the voltages are there or not, and if they're not there, then you can take it from there. There are several different possibilities that could be causing this, and I'll go through some of them. So what we're going to do is we're gonna power it up and do some testing. But obviously you have to be really careful here, because this is, you know, the areas with live mains voltage and the CRT 7 kilovolt or over 7 kilovolt voltages, so you have to be very careful. You don't want to go anywhere near you know, the mains voltages or the CRT 7 kilovolt voltage, because that will kill you. So there are several things that you should bear in mind when you probe on the live circuit. One of them is you always keep one hand behind your back while you probe with another one. That is to make sure that you don't touch two points of the circuit at the same time with the two hands, which would allow the current to flow through your body and through your heart, literally, to the other side, which will increase the potential for the current to cause you an injury or death. So you always keep one hand behind your back, probe with one hand only. Another thing you can do is you can use one of these RCD, which is a residual current device. It will detect if there is any current path apart from the one going from the live to neutral. So if there is a current path, say going from live to earth, it monitors the current going into the circuit through the live and back from the circuit through the neutral. And if there's a difference between the current going through the live and coming back through the neutral of more than 30 milliamps, it will cut off the circuit, and you will have to manually press a button, a reset button, to turn the circuit back on. So although this will not save your life in all the circumstances, it's an extra layer of protection. Okay, so what I have here is a Fluke 87. We have these two probes and one of these little clips which you can just slide onto a probe. And this is handy, as I mentioned, if you only want to use one hand to probe, you attach this to some suitable ground point, and then you can just use one hand and keep the other one behind your back. So I'll just attach this to the chassis, and the first thing I want to measure is the voltage on the filter capacitor on the main board. Now I'm gonna power up the oscilloscope. Okay, and now we're live. Now only one hand. So let's check the voltage on the filter cap. So we have minus 1.38, so that'll be our ground, and 66 volts on the positive. So yes, there is a voltage on there. Okay, so now that we checked that we have some voltage on the main filter cap, which would then feed into the switch mode section, I've flipped the scope on its side, and this is the back or the bottom of the main board. And so what we're going to do is we're going to check that the voltages on every test point are as they should be. And we start with the minus 5.2, measure it. You can see how the fluke is on the voltage measurement, and it's showing nothing, absolutely nothing. So 0 volts on the minus 5.2 volts, plus 5.2, 0 volts, minus 8.6, we go about 200 millivolts or so. It's not good enough. 8.6 volts, that's positive 8.6. We have about 625 millivolts, again not good enough. 38 volt rail, wait, we got some voltage there, 37.4. Now that looks good to me. That looks like we have one rail which is working okay. And plus 100 volts. You have to be very careful there, because 100 volts can kill you. And we've got 36.9. again, that's not good enough. So we have a few options now. Obviously we can assume that the power supply is faulty, but it's not as simple. What you want to do is you want to make sure that none of the circuitry which is after the power supply is causing the power supply to shut down and overload. Now that would happen if, for example, you had a short circuit somewhere in the main circuitry, or a blown up component which would have a, which would have blown in a low resistance mode, so that would draw too much current and could cause the power supply to shut down. Now you can easily isolate the main board here. This is a very good design of the circuit board, because you have wire links here going from the power supply section into the main board section for every single rail, which is brilliant. So what you can do is you can desolder one side of each link, and that way you isolate the power supply section from the main section, and that way you can check whether the power supply comes on when the rest of the circuitry is disconnected. That would mean that there is potentially a fault with the main circuit, causing the power supply to shut down. If, however, you have the voltage measurements exactly the same when you disconnect these links as you have when you had them connected, that means that the power supply is most likely to be at fault, because even when you isolate it, it's still not giving you the correct voltages on the output. So I have desoldered this side of each link, of each rail, and when I measured the voltages, they were exactly the same, so no change there, which means that most likely it is the power supply that is faulty. So we're just going to focus on the power supply section for the moment. This does not mean that the main circuit is not faulty. All it shows us that we have to start with the power supply, because even when we disconnect the main circuit, the power supply is not generating the correct voltage levels. So once we fix the power supply, we can connect the links back. When we check that the correct voltages are generated, we can connect the links back, and then we can take it from there and see whether whether that fixed the entire issue, or whether there is whether there is a problem with the main board. Okay, so the power supply is a switch mode power supply, and you can see the two controller chips here, TL494. It's very nice that they actually put the designator, not just the designator, but the chip model on the silk screen, so you don't have to flip the board over to see what you're dealing with. And so these two, there's two probably, because there are probably two stages of the regulation, and then you have some power transistors up here. So those will be the switching transistors probably. So what we can do here, and lots of passives obviously here, and a op amp. It's a 358, so probably LM358 dual op amp. Now what we can do here is we can check that first that the regulators, the PWM regulators, TL494s, that they're getting the correct voltages on their supply voltage pins, because obviously if they're not getting any power, then they will not function in the first place. So we check those, and then another usual culprit in switch mode power supplies, apart from the dried up capacitors, which which is possible, but they use quite good quality capacitors here, so I don't think that'd be the fault. We can check those later, but the most likely other fault is blown up output transistors, and I can see that they've been swapped already. I can see there's some different soldering from the factory soldering on the rest of the board, so I can see someone has played around with this already. So I have downloaded the datasheet for the TL494, and basically what we're looking for on this diagram is you want to have a look at what you can measure. Okay, let me just move this there. And so what you can measure here is you can measure the You got ground here and VCC, so you can measure the supply voltage against ground. And you can also measure the reference voltage. So the supply voltage measurement will indicate, will show you whether the chip actually has any chance of functioning. And if there is a supply voltage on it, then you can measure the functionality by measuring the reference. And you can see here that the chip provides a 5 volt reference. So the reference pin should be showing 5 volts, and if it is, then you can check whether the CT pin, which is the oscillator input capacitor, whether that pin is switching. Now it should be a sawtooth on the CT pin, so that will look something like this. Okay, so that should be a sawtooth signal on the CT pin. What you can measure up on the output section here is to make sure that these are actually switching. So those will be switching at the preset frequency. So if you measure say 100 kilohertz on the CT pin, the oscillator pin, then these will be switching at 100 kilohertz, and it will be switching. This will be the pulse width modulated switching already. So there's a few things you can check, and a few ways you can verify that these chips are functional. And again, it can shift you forwards in your troubleshooting to see you know, what to concentrate on. So first, let's have a look at the VCC pins against ground. So that's pin number 12. So let's have a look at that. So we need to find pin 12. So remember this is in reverse because the chip is on the other side. So pin 1 is up here, and pin 12, since this is a 16 pin package, there will be 8 pins on this side, 9, 10, 11, 12. So that's pin 12 here, and we have 34 volts on pin 12. That's supply voltage. So we have a supply voltage on this one, and the other one, pin 12, so 9, 10, 11, 12 here. Yep, 37.4. Now that shows us that the chips are being powered, and therefore, you know, they can function if they if they are fully functional. The next thing I'm going to measure is the 5 volt reference. That's the second easiest thing to measure, and the 5 volt reference is on pin 14. So I don't know if you have the data sheet in front of you, or you can check back on the one I showed you before. Pin 14 is right up here, so that'll be 15, 16, so 14 is just here. Okay, so I got 3.627. So that's weird, but that could be, I remember the filter cap was about 1.3 volts down, so that could be that the reference is slightly lower, the ground reference. So let's have a look at our ground point, 7, pin 7. So there you go. Yep, so the ground point is minus 1.34. I would stick 2 probes in there, but that's not a good practice. It's not a good idea to probe with 2 probes, especially when you have live mains around there. So we're just gonna do simple addition. So you go 1.346 plus 3.627. It's close enough to 5. So yeah, I'm happy with that one. That's 5 volts on that one. And this one here, 5 volt one. There you go. Oh, and there you go. 0 volts on that. Let's just double check. That's pin 14. Yep, there's 0 volts on that. And let's check the ground. That'll be pin 7. And 0 volts on ground. So the ground is ground, as you'd expect. But the 5 volt reference is not outputting anything. So that, you know, it's possible that this chip's faulty. Actually, it's very likely because you would expect 5 volt reference on that pin. I am going to measure the the waveform as well, just to double check, and maybe, you know, it is interesting. So we'll have a look at the waveform. Okay, so what I have here is I have my scope. It's a PC based scope. I attach the ground lead to the chassis, and my probe. I'm gonna have a look at the CT pin. So there'll be the, let me just connect this. Okay, so the CT pin would be pin 5, and we'll have a look also on the output transistor pins. So these are collector 1 and 2 and emitter 1 and 2. But let's have a look at the CT first. So that would be the capacitor of the oscillator. As I mentioned, there should be a sawtooth waveform on that one, if it's switching correctly. So let's attach the ground to chassis, and a CT of the first one, which we found to output the correct 5V reference as well. There you go. I hope you can see that. It's perfect sawtooth signal. You look at the screen, and the output, which ones? Pins 8, 9, 10 and 11. So yep, pin 8, we've got a PWM signal on pin 8. Let me just change the scale there. I'll do plus minus 50 volts. So there you go, pin 8, beautiful signal on pin 8, so that is switching very nicely. So let's have a look at the second chip, which we found to be faulty. I'll change the scale back, and the CT is pin 5. So I got 1, 2, 3, 4, 5. Wait, and that doesn't look very good. I don't know if you can see that. Let me zoom in. You see that? That's not a good sawtooth. It's cut off at the top, so that doesn't instill much confidence. And the outputs, let's check pin 8 again. Oh, here it is, sorry, pin 8. There's some switching going on, but it's, you know, that's nothing. I'll zoom in. Plus minus what, 2 volts. Yeah, no, that's not good. That's not what it's supposed to be. Let's measure the 9, 10 and 11. So 9, 10 will be connected because those are the emitters, and the collector 11. Yeah, now it's not even switching. It's just a noise. Even with the probe disconnected, you can see the noise there. So yeah, that chip's definitely faulty. So that sounds like a good lead to me. I'm gonna order the chip, and I guess I split this video in 2 parts. And once I get the chip back in, I'll do a repair video and we power it up and see whether that fixes the problem. You know, you never know. It might be just as simple as a 50 pence chip to be swapped, or it might be something else horribly wrong, and we may not even be able to repair it.